Okay, now more, well, the table's a bit too close. Between me and the camera, the tripod, is a dining room table. Okay, give me a bit more space. I'm still experimenting on a procedure. I keep trying different things. Okay, so more definitions in the context of graph theory. So quite a few. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So nearly a dozen definitions in this session. And then next session we will change topics, get away from graphs, and start talking about strings of symbols, like a binary string, a string of letters, and whatnot. Okay, so path. Well, pretty much common sense. So what is a path? Well, I'll give you an example. How would you get from this node to this node? Well, you would follow a path. So you want to get from this one to this one. Well, you go root, 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 root. Okay? That is an example of a path. So, common sense. So what is a path in terms of a definition? Well, it's a sequence of nodes, right, connected by edges. That's what it says here. Right? Now, if you had if you were not allowed to go up, you could only go down, then you could not get from here to here. But you could get from here to here. Right? You just go droop, droop, droop. That would be your path. So the concept of a path in graph theory is pretty intuitive, right? Fairly easy. Okay. Now there's certain kinds of path. What's a simple path? A simple path is one where there's no repetition of nodes. Like each step you go to a new node that's not been touched before, in a sense, right? Which is a simple path. So no repeated nodes. Say you had nodes like in the form of a figure of 8, like this. Then as you're going down the path, to do the full 8 figure, the node in the middle, there, you would go through it twice. So that figure of 8 path is not a simple path, okay? Because that node in the middle, where the two zeros touch, making the 8, so to speak, that gets touched twice, gets repeated. So therefore the path is not a simple path. Okay, connected graph, what's that? Well, intuitively it sort of means there are no nodes that are strangers, isolated. They are not disconnected. So any 2 points in the graph, there's a path between them. Okay, you can get from one node to any other node in the graph if it's connected. Right. So any 2 nodes have a path between them. That's the definition. Okay, what's a cycle? Well, again, a lot of these definitions are intuitive and sort of obvious. What is a cycle? Well, it's a path, but one of the nodes, or the start node, wherever it is that you're starting, is also the end node, right? So you're looping, so to speak. You're cycling. You've created a cycle. Okay, so a cycle. It's a path, and the start and end, it starts and ends on the same node. So like start here and come back. So you formed a loop of edges. in a sense. What's a simple cycle? Well, it's a cycle. It has to have 3 or more nodes. Like if you had 2 nodes, well, it's just two nodes in a connection, right? It's sort of not exactly a cycle. And maybe you could do this, could you? Yeah, but it's not generally intuitive idea of a cycle. Okay, so a simple cycle, it's a cycle. You need at least three nodes and only 1 repeated node. Okay, so if you want an example of a non-simple cycle, well, that figure of 8 one I gave you just before, right? Because you have, like you start here, let's say, and you go, so you end up where you started with, so it's a cycle, but that node in the middle, so to speak, you've touched it twice, so you've repeated it. So there are 2 nodes that are repeated, the upper one where you started, and that middle one. Okay, so that figure of 8 would not be a simple cycle. Okay, a tree. What's a tree in the context of graphs? So it's a connected graph. Right? That means any 2 nodes, there's a path between them. Right? There are no isolated nodes. There are no disconnected nodes. And with no simple cycles, like there's no looping. Right? So this is an example here of a tree in the technical sense in graph theory. Okay. So yeah, I mean, you can see it's connected, right? You can connect any 2 with edges, so it's connected. There are no cycles, right? There's no looping in a sense. Now, trees get used a lot in computer science, and if you've done some computer science, like undergrad computer science, you'll know that's true. Trees get used a lot. So there's a whole slew of technical terms, defined terms, relevant to trees. I'll just give you a few, well, 2 I think. It's from the text. The top level node, and then you descend and descend. That's typical of trees. You just keep going down. Now the top node here tends to be called the root, because it sort of looks a bit like a root system. It's the beginning of a root system of a tree. Now you may say the whole thing is a tree, which is sort of stupid. I've always wondered why this thing is called a tree. Why is it called a root? Right? Because it's usually drawn top down. But I suppose you could look on it as a tree if you in your mind's eye, so to speak, you did this and you turned it upside down. And it would still make sense that this is the root node, right? Because that would then be the bottom of the tree where the root starts. But anyway, that whole thing is called a tree, which is sort of silly, but we're stuck with it now because it's so conventional. And the top node here is called the root, right? Now these bottom ones here, well, not exactly, but I mean the nodes whose degree is 1, except for the top one, except for the root. That's the one exception. But these nodes here that have degree 1. Remember what that means from earlier session? What's the degree of a node mean? It means the number of edges that connect to it. Maybe that was the verb I was looking for. Connect to. Seems intuitive, right? So for this tree, count the number of leaves. Leaves are the ones that only have degree 1. So there's only 1 edge that connects to that node. Those nodes are called leaves, except for the root node. Don't forget that. Right? So how many leaves, degree 1 nodes in this tree? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 9 leaves. This tree has 9 leaves. Okay, so now I talked a bit before, two sessions ago, 1 or 2, the notion of a directed graph. So far, I think, is that true? So far we've been talking undirected graphs. In other words, the direction from one node to another along an edge was not important, was irrelevant. But in cases where it is relevant, for example, if you had a network of oil pipelines, or say you have a map of downtown, the old town, say a European city or something, with lots of one-way streets